Hello everyone! In this lesson we will be exploring the stability of multi-hull vessels, focusing on two critical factors, metacentric height and hull spacing. These play a key role in determining the performance and safety of vessels such as ferries and offshore platforms. Hello everyone! In this lesson we will be exploring the stability of multi-hull vessels, focusing on two critical factors, metacentric height and hull spacing. These play a key role in determining the performance and safety of vessels such as ferries and offshore platforms. To start, let's think about a real-world scenario. Imagine a ferry sailing across rough waters with waves crashing against it. Despite this, it stays upright. How does it maintain stability? Now consider an offshore oil platform. It supports heavy equipment and endures extreme weather conditions, yet it doesn't tip over. Again, why is this the case? In this lesson, we will answer these questions by breaking down the key stability principles and analysing how hull spacing affects metacentric height. On the left, we see two different stability mechanisms. Let's think about a real-world scenario. Imagine a ferry sailing across rough waters with waves crashing against it. Despite this, it stays upright. How does it maintain stability? Now consider an offshore oil platform. It supports heavy equipment and endures extreme weather conditions, yet it doesn't tip over. Again, why is this the case? In this lesson, we will answer these questions by breaking down the key stability principles and analysing how hull spacing affects metacentric height. On the left, we To understand why vessels stay stable, we need to focus on three key concepts: buoyancy, centre of gravity and metacentric height. Looking at the diagram, we can see how these forces interact. The buoyant force, labelled B, pushes upward, counteracting the vessel's weight. The centre of gravity, labelled G, is where the vessel's mass is concentrated. If G is lower, the vessel is more stable, but if G is too high, then it becomes top-heavy and more likely to tip over. Now notice the metacentre M in the diagram. When a vessel tilts, the centre of buoyancy shifts and the new buoyant force acts through M. The distance between M and G is called the metacentric height, or GM. If GM is large, then the vessel has high stability, meaning it resists rolling, but it may have a stiff, uncomfortable ride. If the GM is small, the vessel experiences more rolling, making it less stable and increases the risks of capsizing. Now let's see how increasing hull spacing affects metacentric height. The equation Bm is equal to I divided by V tells us that Bm, the metacentric radius, depends on I, the second moment of area, and V, the displaced volume of water. Since Bm is proportional to B squared, which is hull spacing, increasing hull spacing increases Bm, which in turn increases Gm. And this is summarised in the table on the right, where a wider hull spacing leads to a higher Bm, which results in a higher Gm and greater stability. However, while the vessel resists more rolling, it also leads to a stiffer ride, which can be uncomfortable for passengers. And this is why it's used in offshore platforms and sometimes ferries, where stability is prioritised. However, a narrower hull spacing results in a lower Bm, leading to a lower Gm and reduced stability. This allows for more rolling, making the ride smoother, but increasing the risk of capsizing in rough conditions. Examples include racing trimarans and speedboats, where agility and speed are more important than extreme stability. One of the best examples of extreme stability is the Hibernia oil platform in the North Atlantic. This structure must withstand massive storms, waves and icebergs while also remaining stable. To achieve this, it has a large hull spacing, which in turn increases GM and prevents tilting. Its multi-hull design distributes wave forces evenly, ensuring it remains upright in rough seas. Now let's apply what we've learned with a numerical example. The question is, A multi-hull vessel has an initial hull spacing of 10 metres and a metacentric height of 0.8 metres. The height of the centre of gravity is 1.5 metres. If the hull spacing is increased to 20 metres, what is the change in GM? On the left, we can see the label diagram. Now let's apply what we've learned with a numerical example. The question is, a multi-hull vessel has an initial hull spacing of 10 metres and a metacentric height of 0.8. Step 1 wants us to calculate the initial BM. We do this using the formula GM is equal to BM minus BG. However, we rearrange it in the form BM is equal to GM plus BG. We plug in our values of 0.8 and 1.5 to get an initial BM of 2.3 metres. For step 2, we then calculate the BM after increasing the hull spacing to 20 metres. Using the formula BM is equal to I divided by V, we know that I is equal to B squared times length divided by 12, and we know this from the standard second moment of inertia of area for a rectangular section. We also know that V is equal to L times D. So using these, we then get a formula for BM in the form B squared divided by 12D, which we can now solve for D. So we plug in our initial BM of 2.3, our initial hull spacing of 10, and we get a value for D of 3.62 metres, which then allows us to calculate the BM after increasing the hull spacing, where we plug in a new hull spacing of 20 metres to get a BM of 9.21 metres. For step 3, we then calculate the new GM using the formula GM is equal to BM times BG. We plug in the value of 9.21, which we just calculated, and the 1.5 from the question to get a final answer of 7.71
To do
metres.
these calculations, step 1 wants us to calculate the initial BM or metacentric radius. So we know the formula GM is equal to BM minus BG. However, we rearrange this to get BM is equal to GM plus BG. We plug in our value of 0.8 and 1.5 to get a final answer of 2.3 metres for the initial metacentric radius. Step 2 is to calculate the metacentric radius after increasing the hull spacing to 20 metres. To do this, we use the formula BM is equal to I divided by V. And from the standard second moment of inertia of area for a rectangular section, we know that I is equal to B squared times length divided by 12. Then we know that V is equal to L times D. And we plug this into the formula, and then we get a new formula called BM is equal to B squared divided by 12D. In this, we want to solve for D, so we plug in 2.3 from the initial BM, our initial hull spacing of 10 metres, and we get a final answer of 3.62 metres for D, and the D stays constant. So now in the second half of this step, we have BM2 is equal to B2 squared all over 12D, where the hull spacing will increase to 20 metres, and we plug these in and get an answer of 9.21 metres for the second metacentric radius. The final step is to then calculate the new GM using the second metacentric radius and the centre of gravity. So for that, we use GM is equal to BM minus BG. We plug in 9.21, which we calculated, and 1.5, which you are given in the question, to get an answer of 7.71 for the final GM.
From this, we can see that hull spacing plays a crucial role in stability. As seen in our calculations, increasing hull spacing from 10 metres to 20 metres raised the GM from 0.8 metres to 7.71 metres, making the vessel much more stable but also creating a stiffer ride. The graph on the left clearly shows that as hull spacing increases, the GM rises exponentially, meaning that even small increases in spacing can lead to significant stability improvements. This is why ferries and offshore platforms have wide hull spacing to resist rolling, while racing trimarans use narrower spacing for better manoeuvrability.
The graph on the left clearly shows
Looking
that
at the table on the right, we can see that ferries balance stability and speed. Offshore platforms prioritise maximum stability with very wide hull spacing, and
This is
racing
why ferries and
trimarans
offshore
optimise
platforms
for
have
speed
wide
with
hull
moderate
spacing
stability.
to resist rolling,
In
while
ship design,
racing
hull
trimarans
spacing
and
can be
speed
carefully
boats use
adjusted
narrower
to match the
spacing
vessel's
for
purpose,
better
ensuring the right
manoeuvrability.
balance between stability,
Looking
speed
at the
and
table on
comfort.
the right, we can see that ferries balance stability and speed. Offshore platforms prioritise maximum stability with very wide hull spacing, and racing trimarans optimise for speed and moderate stability. In ship design, hull spacing can be carefully adjusted to match the vessel's purpose. We can now apply these to a real-world problem. Imagine designing a high-speed passenger ferry for the North Atlantic, where waves can reach up to 15 metres. Consider the following questions. What factors should be considered when choosing hull spacing? Is a very wide hull spacing always the best solution? Why or why not? We can now apply these to a real-world problem. Imagine designing a high-speed
These are the key insights when designing multi-hull vessels. When choosing hull spacing, a higher GM and wider hull spacing can both improve stability, however they can also make the ride too stiff. So a moderate GM gives a nice balance between comfort and stability. Is wider always better? Well, often too wide can mean stiff and uncomfortable, so a moderate hull spacing allows for some rolling while making it a smoother, more comfortable ride for passengers. When comparing ferries and offshore platforms, ferries prioritise a smooth ride, so they need moderate GM for passenger comfort. Offshore platforms,
These
however,
are the key
require a
insights
high
when
GM
designing
for extreme
multi-hull
stability
vessels.
during storms.
So, when choosing hull
To
spacing,
sum everything up,
a higher
the
GM
stability of multi-hull
and wider hull
vessels
spacing
definitely
both improve
depends on
stability,
net-eccentric
but
height
they
and
can
hull
make the ride
spacing.
too stiff and lead to
Engineers
jarring
must be able to
motions.
balance
So a
stability,
moderate
comfort
GM
and
can
efficiency
balance
when
comfort
designing
and
vessels
stability
for
much
different
better.
purposes.
Is wider always better? Then too wide can mean too stiff and lead to an uncomfortable ride, so a moderate hull spacing allows for some rolling while making it a smoother ride. Then, when comparing ferries and offshore platforms, ferries prioritise a smooth ride, so they need a moderate GM for passenger comfort, whereas offshore platforms require a high GM for extreme stability during storms or extreme weather conditions. To sum it all up, the stability of multi-hull vessels depends on metacentric height and hull spacing. Engineers must be able to balance stability, comfort and efficiency when designing vessels for multiple different purposes.